formula when it's falling from its starting point of 0?
If you're dealing with something that's thrown up into the air, you would treat it as two parts. So you got the part from moving to rest, and then rest to down.
Okay. And then the 5.7 in this equation would be, in number 8, it would just be the Mars gravity, right? Not the 5.7.
Right, in the actual master set, I think it's 3.7 meters per second squared.
Okay.
Jasmira?
So if you're throwing something up, the initial velocity would change from, say if I throw something up and it's like 20 meters, it'll be 20 meters instead of 0, because 0 is from falling down. Did I confirm?
So if we had thrown the object up in the air and I wanted to figure out how much time does it take to actually get to the ground?
Yes.
So the whole thing is doing that.
Yeah.
Be very careful about using that formula. Actually, be careful about using either of these.
Yeah.
I'm gonna say it depends. So if this were physics 151, we would use the more generalized equation than this. We would use delta x is equal to VIT plus 1/2 AT squared. That's a more generalized constant acceleration equation, and there's a video where I talk about it.
That's what I learned, that's how I actually learned how to do this. I get the same answer, but instead I take the initial velocity and that's a 0, so it cancels out and it's really just a 1/2 acceleration time t squared.
Right.
And I use that and I get the same thing.
Yeah, and you should. And if you throw the ball into the air, or the object into the air, so the initial velocity is not 0, and how long does it take to get down to here? Your displacement in the end is still negative 20, or positive. It's 20 meters, positive or negative, depending upon which way you say it's positive.
Yeah, you just replace the time into the equations and get your answer.
Yeah. If there's an initial velocity not 0, you're end up most likely using the quadratic formula, which for some of you will bring back some happy memories, no doubt.
So basically, even if you throw it up and it arcs, the displacement would be the same as if it were just dropped because.
Yes.
Okay.
That's the beauty of displacement versus distances. You don't care what happens in the middle. All you care about is where do you end up relative to where you started. There are times when vectors make life simpler.
So when something is thrown, that's the formula?
You could use this one, yes.
Okay.
This actually also works for the cars moving along with straight line problems too. And I've seen on tests, I'm not assuming that students will be using this formula right here. Or if I do put this in there it would be like one part of a multi-part problem where the impact is insignificant if a student looks at it and has no idea what to do.
Yeah, I'm able to understand that one a lot better than the one.
Okay, if you're good with that, excellent. Other questions before we actually get to solving for time? All right, so time. We need to get time all by itself, or time. First, we need to get time squared all by itself, so we have to get rid of this stuff up front. The two basic approaches is we multiply both sides by 2 to get rid of the 1/2, and then we divide by 5.7 to get rid of the 5.7. Or you could, if you wanted to, multiply these two together first, and then divide by whatever that is. Okay. It's a matter of your own personal math style. So I got 20 is equal to, I'm just going to go ahead and multiply, do 1/2 times that, which is 2.85, I believe. And then divide by 2.85 to get rid of that. So I'm left with time squared is equal to something. Somewhere around 8. What is it? 7.0175. Okay. And we still need to solve for time. That's time squared. And so we have to get rid of the squared here, and you undo a square with a square root. So we take the square root of both sides. And that will end up being 2 point something.
649.
And at this point, since the question actually asked for time, don't forget the units. So the next part was, what is the velocity just before it hits the pavement? And again, we can go to a Hewitt formula. There are a couple ways of doing it. Since time is not an integer, setting up the chart's gonna be a little bit trickier. But in the, I think it's the section before he has this formula, he's got, that's where he does the speed acquired is equal to GT, something like that. Change in speed is equal to GT, or making it more generalized, change in velocity is equal to acceleration times time. And just a side note, I am aware that sometimes it looks like alphabet soup up here. It's all part of the physicist's desire not to write out words. I could have also written this as the change in velocity is equal to acceleration times change in time. If it becomes really annoying, I can explain why I can just drop the delta in front of the T, but in essence, they mean the same thing. You can't drop the delta in front of other letters, but you can in front of time, as long as you understand that this T right here represents how much time took place while whatever was happening.
So those are all the same thing.
Yes, this is, the way this is written, the way Hewitt describes it, it's specifically for, I have an object, I drop it, and it falls. This is more generalized because I'm using, in general, acceleration. And this is more formal with the delta T. But yes, they in essence mean the same thing. So now, because this applies to specifically, I drop an object, how fast is it going? That would be 5.7 times time, which is 2.649. Around 15-ish. Now that is the change in the speed, or let's use better wording, that's the change in velocity. But I start out at 0, so that's also my final velocity. That's how fast I'm going just before I hit. And so, looking into this one, change is always whatever the final value is minus the initial value. That's equal to 15.099. That's 0, because it dropped. Therefore, the final velocity is 15.099. And don't forget the units. I think I heard it. There we go, definitely heard it that time. Pardon?
You don't divide by 2?
No, not for the question I was thinking was, what's the final velocity, or the velocity just before it hits?
Oh, that's average, so to get the average velocity, that's when you divide by 2.
We're gonna be dividing between the initial and the final. We're gonna average the initial and final. We have start at 0, we go to 15.099, so we'll be averaging those two numbers in the next part.
Oh, the initial and that.
And that, yeah.
Okay.
Which brings us to the next one for average velocity. There are two ways of finding average velocity. One way is always true. No matter if you're doing calculus-based course or conceptual physics, the average velocity is always going to be the displacement divided by time. So we could, instead of the way that Jasmira was just outlining, which is also valid in this case, instead of doing it with the averaging of the velocities, you could just do, well, it went 20 meters in 2.649 seconds and get an answer. If acceleration is constant, then you have another way of doing it. So this is always true by definition. And And then if acceleration is constant, which it is for a free fall problem, ignoring air resistance, then my average velocity is just my initial plus my final divided by 2. So that was 15.09099 divided by 2. So 7.5.
7.55. And that's your average velocity?
Yes, while it's falling.
Wow.
So that's the initial and the what?
Final.
This is initial and final.
Okay.
In class last week, we talked about, there's nothing special about averaging every second. You could average every 2 seconds or 3 seconds, or why not whatever the time is for the duration of the problem.
And then divided by that amount.
Yes, yeah, and since there are only 2 numbers here, divide by
That
2.
makes sense.
The biggest mistake I see students make on a test for a problem like this is they sort of blend the two and they add the velocities and divide by time, which is not anything other than the wrong answer.
So when did our test be? When did our test finish? When are we gonna have our test?
I forgot what the schedule says.
Just next week, I think.
February 3rd, I think.
Which I think is next Thursday.
Okay.
Yeah, it is February 3rd.
Of next week. So the Thursday of next week.
Yeah.
It might get pushed. I have to put something down. It's not till I actually have students in front of me that I have any sense of what the pace should be. So it might or might not be Thursday of next week. It will not be earlier than that. And just from a language point of view, and apparently I'm in the huge minority on this one. Today's Tuesday. When you say next Thursday, I think 2 days from now. And most people call that this Thursday. Next Thursday is implied next week. That's not the way my mind works. So, to me, next Thursday is the next Thursday we come across, which is 2 days.
Do you have like study guides for tests?
Well, the master sets, there are old tests also posted, some with solutions, where solution being, I've written out, all the steps, some with just the answers.
Okay.
And then I think there's some posted with neither, just there for decoration. Or if you wanna try it. Now, some of the tests, if you work on the test that doesn't have answers or solutions, then you can say, hey, what's the answer to such and such, or
Alright.
could you give me a solution? I had a student a couple years ago, probably more than I'm thinking right now, who came into class one day with a list of, here are the tests and here are the problems I'd like to see solutions for. And he just gave me a list of the ones that he had worked. And so I wrote it out by hand, took pictures, posted it.
Before our next test, could we have another Zoom study session? Because that really changed how much I understand this class. Like, maybe during one of the office hours, could we have a Zoom session?
I'm not opposed to that, yeah. I probably shouldn't do it more than just one office hour. At least last time, since it was class time, I knew everyone in theory had it free. Assuming you had power. So, yes, if you would send me an email, and it could be, abrupt, like, come on, man, where's the Zoom office hours sessions? Something like that.
I would also be interested in that.
Yeah, I would get on
Okay.
there.
So right now, I guess I'll schedule it for just when the office hours are. And if there are other times where I need to do it before the test, then, I'm open to that. Obviously, I can't do it if I'm in class.
So it wouldn't be this Wednesday, but maybe next Wednesday, or?
Yeah, that, feels reasonable. I just have to remember. And my memory is not getting better.
We'll remind you Tuesday.
So Tuesday, I have very brief office hours, so I would need to, I assume you want something more than just that half hour before class.
Oh, no, I was saying we'll remind you Tuesday before the.
Oh,
Wednesday
thank you,
in
sorry.
class.
I thought you were pushing for a Tuesday.
No. Tuesday, 3 to 6 is plenty.
Would you record it and post it? 'Cause-
That is the plan.
okay,
The last Zoom session I posted, and it's under, if you go to coursework chapter 2 or 3, whatever, okay, I guess you found it. I did get an email from Zoom or the administrator, the automatic message that said, if you want students to be able to see this, give them this address, and they had this long thing typed out, and I thought, oh, this time I actually did check. Let me cut and paste this into, and see if I can get to it, and it kept giving me the message of, that recording does not exist. So that's why I downloaded it and then put it on YouTube. I think, that one, it's an unlisted address, so. It's being shared with anyone who randomly guesses what the IP address is. All right, so the next part of this is, what is the average velocity when it stops? Well, how fast is it going when it first hits the pavement?
0.
Not when it first hits.
That, would it not be-
7.55?
Yeah,
Oh, nope.
okay, well then it's the other one.
Yes, it is.
15.099.
That's how fast it's going just before it touches. In physics, we don't make a distinction between just before it touches and when it first touches. And potentially I'm gonna contradict myself when we talk about number 16. But in terms of an actual quantity, the difference in speed between just before it hits the pavement and when it first touches the pavement is so insignificant, we consider it the same number. So in the second part of the problem, it starts out going 15.099 meters per second, and then what's the final speed or velocity?
0.
Because it stops. So, now the reason why this is I'm treating this like a separate problem, other than the fact that there's this link right here, is the fact that the acceleration changes. A lot of what we do assumes constant acceleration, and it's constant acceleration until it hits the pavement, but once it hits the pavement, it's a different acceleration. In the assumptions I said, assume that it is constant as it's stopping, because otherwise it's a calculus problem. So what is the average velocity?
7.55 meters per second.
Yes, it's the exact same. The only difference mathematically, if you want to make an argument for it, is the first time we did 0 plus 15.099 divided by 2. Now we're doing 15.099 plus 0 divided by 2. But the average velocity is the same as it was before. The time to stop, well, I gave you how far it goes in our spongy example right here. So I know the distance, or let's do the vector terminology. I know what the displacement is. It's going to be 8 centimeters downwards, positive. That's equal to the average velocity times time. The formula, the base formula that we're working with there is that we can, a little bit of stunning visual effects here. Oh, actually the other formula right there, the average velocity is displacement divided by time. We know average velocity, we know displacement, it's a matter of solving for time. So time, delta t or t, is going to end up being my displacement divided by my average velocity. Be careful of units, that's 8 centimeters right there, but my average velocity is in meters per second. So I'm gonna put that 8 centimeters in terms of meters, so that's 0.08 meters divided by 7.55 meters per second.
What are you trying to find out? I'm sorry.
Yeah, I'm confused.
How much time did it take to stop? Once it touches the pavement, how much time did it take to stop?
So you got the 0.8 from the 8 centimeters.
Right,
Okay.
0.08.
What is that time?
This is the amount of time it took to
That
fall.
would've been this time.
Wait, which ones are all tied to the phosphorus?
Right, so there's basically two parts of the problem. First part of the problem, it's falling. Second part of the problem, it's stopping once it hits the pavement. So as this thing fell, it took 2.649 seconds to fall. It was going 15.099 meters per second at the end of falling, or just before it hit the pavement, at an average velocity of 7.55 meters per second. It hits the pavement, and so now we have a different constant acceleration.
And you said the red is the time it took to hit the pavement,
The red here is the time it takes to stop.
to stop on the pavement.
Yeah. It should be really quick. Most things when they, you're falling 20 meters, so. Is that a 6-story building? You're falling off the top of a 6-story building, it takes a couple seconds to fall. And then you hit the pavement below, it's gonna be very quick. So the time here is gonna be a really small number. 0.08 divided by 7.55.
Why did you turn it into 0.08?
Because my average velocity is